That same year, we have GoogLeNet, which was published. And again, you can see GoogLeNet, this is really how they spell it out. So it's GoogLeNet. So it's really, again, a nod to LeNet. LeNet was very much an inspiration to a lot of these papers. And they published an even deeper model with even less parameters and higher accuracy. And again, it was the same year. And these two models are both very much important. And again, the memes are very real. And in this case, they actually quote this meme in their paper. If you look at the references, the first reference is "we need to go deeper" meme. They reference it, they don't even hide it. They say we codenamed our model Inception based on this meme. So yeah, again, in 2014, people loved memes, so I thought it was pretty useful to mention this in this talk. So yeah, let's look at this network. So this network can be a little bit daunting when we look at it. It's pretty big, and so there are a few operations involved. We have the convolution operation. We now have a concatenation operation, which essentially means stacking the outputs together. So it's this concept of depth. If you have multiple feature maps and you concatenate them, you're just adding more depth to your network. We have the max pooling, and we have the softmax operation. Now again, this network looks really big and intimidating, but really what you notice if you look closely is that you have these modules that show up. And these are what they call the inception modules. So these modules, Gaetan mentioned this earlier, it's really useful to be able to define in our network sets of modules that can be reused. And in this case, we have this module show up at multiple times throughout the network. And in fact, if you look closely, you'll see that we have a total of 9 inception modules. So while it looks very complicated, it's the same module over and over being reused. And what was very interesting is that in their inception module, they had parallel convolutions in each layer. So let's look at this module a bit more in depth. So here we have, it actually goes from bottom to top, so this might be a bit confusing. So we have the previous layer, our input, and then we do, in parallel, a series of different convolutions. So they add these one-by-one convolutions here, which we talked about one-by-one convolutions earlier today. And the motivation behind the one-by-one convolutions was to reduce the number of parameters that they had to use in their model. So we'll see that this model actually uses a lot less parameters, and this was in part due to this wise decision to put in the one-by-one convolutions. And what's really neat as well is that you can see that they use a combination of both 3x3 and 5x5 in this module, as well as even some max pooling and one-by-one convolutions, and simply just some one-by-one convolutions. So the reason behind this was that they wanted to let the network decide which features were more important at different stages. Instead of saying at a specific stage you're only using this 3x3 filter or only using a 5x5 filter, they wanted to let the network have the option to choose all of them and combine them with this concatenation at the end, and then pass this information onwards. And another reason to use these one-by-one convolution, so they mention in the paper, besides being used as reductions, you can also add a ReLU activation to it, making them dual purpose. So it also helps your network to become a lot more powerful in that now you have these nonlinear activations spread out throughout your network. So GoogLeNet managed to squeeze more layers. So in this case, GoogLeNet had 22 layers and significantly less parameters than VGG. So if we look at VGG, we have about 144 million parameters, whereas with GoogLeNet, we have much fewer parameters. In fact, even less parameters than AlexNet, with many more layers. So already you can see how this arms race was sort of proliferating, and that was how do we get deeper models with less parameters and get higher accuracy.